All right, let's get started. So we finally made it. We're going to do the Carnot cycle today. We do lots of handwork, so we don't really have to have a lot of top hats to keep you engaged. We can get your pencils out, sharpen them up, maybe a calculator or two, and we'll jump in. So last time we talked about adiabatic expansions, and so now we're going to combine them with isothermal expansions and compressions, and we're going to go through a full cycle. So here's our Carnot cycle. The Carnot cycle is the most efficient cycle where everything's reversible. Next time, we'll start looking at actual engines, the diesel engine, the gasoline engine, and the turbojet, and we'll see that they're not exactly a Carnot cycle. They're close in some aspects, but the most efficient one we could have was if every leg was reversible. And so we have the isothermal reversible and adiabatic reversible legs. And so here's all of the equations. We're going to use these today, so we'll get familiar with them as we go through. But we have just these various criteria. If it's isothermal, the definition of isothermal then is delta T equals 0, and that means that the internal energy is 0. And so if we calculate the work, then we can calculate the heat that flowed into the system. So here's our work equation. We have the volume at point B, and the volume at point A is our final and initial volumes. We have the hot temperature, which is the isothermal temperature for that, and then the number of moles and the gas constant. For this gas constant, we'll use the joules per mole gas constant. And then we'll just change the sign of that number, and that's the amount of heat that came into the system. The adiabatic expansion, since it's adiabatic, this is the definition of adiabatic. So the heat is 0. And so therefore the work is the internal energy change, and the internal energy change is the final temperature minus the initial temperature times the heat capacity at constant volume. So that's one place where you can make mistakes, is not having the correct heat capacity and using the CP instead of the CV. So for internal energy, it's the CV. Then we just do those same two calculations, but with different final and different initial volumes and different final and different initial temperatures. Since they're both, there's two isotherms and two adiabats, we just have to have correct finals and initials, and we have the same equations. Then at the end, we can go through and look at the work that we did. We will get some work out of this first expansion and the second expansion, and then we'll have some work that goes back in to compress things. Now, it's easier to compress a gas that is a lower temperature, and so we'll put in work, but it'll be less work than what we got out. So this engine going to the right, going clockwise, will produce work and take in heat. Okay. What's interesting is it will take in heat right here. This AB, QAB is the heat that goes in. And then we get the work out in step 1 and step 2. We have to reset it, so we have to take some heat out at step 3 to keep it isothermal as we compress it, and that's waste heat. So that is lost, and then we have this last adiabatic step to reset it for this compression. Now, what happens if you run this backwards? So if we compress on, this is sort of a side trip, if we compress it on B to A, if these arrows are going backwards, we're compressing things at a higher temperature, and we're expanding things at a colder temperature. And if we run this backwards, we have a heat pump. We're putting in work, and we're pumping heat in a direction. So this running spontaneously produces work and takes in heat. It takes in more heat than the work it produces. Going the other way, we put in a certain amount of work, and we're actually pumping heat. So that's where our refrigeration comes in. So we can turn this thing into a heat pump and pump heat from the cold side to the hot side, or from the hot side to the cold side. If we're going from hot to cold, it's spontaneous because heat flows from hot to cold, and we have a heat engine. But if we pump it the other way, we put in work, we could pump heat from the cold side to the hot side. Okay, and that would be a heat pump, and we could use that to make the cold side colder. And that would be how we do refrigeration. So we could use this engine type idea to do refrigeration, which is pretty fun. Yes?
For the isothermal expansion equation, since delta U equals 0, every equation I found online when I did the homework said delta U equals Q minus W. But if you rearrange it on that board, it says Q equals negative W.
Yeah, so delta, so the first law, one of the statements of the first law is Q plus W. And since this is equal to 0, then we rearrange this, so then Q is equal to minus W. So that's how we got to that part right there.
Is there a reason I'm finding equations that say it's delta U equals Q minus W?
No. Unless they're messing up and then they're saying that one of those signs is negative and they're like bringing it out. But no, these, either one of these can be negative inside. Like you could have a negative Q, and you could have a negative Q and a negative W, and then your delta U would be negative. Yeah. But yeah, this is the statement of the first law, that the way the energy changes is either by heat or by work or both. Yeah. Yeah. So okay, so let's work on the first step, and that is complete the state variables table. So I went ahead and got on the little Trans Am engine modification calculator, and I calculated for this stock engine a 400 cubic inch engine and the compression ratio of 8.38 to set up this Carnot cycle. So we'll do all the calculations for this. Now we have our equations for volume A and volume C. So up here we have our delta V. So that's 400 cubic inches. And our compression ratio was 8.38 minus 1. Okay, but I don't like cubic inches. So what are we going to do for that? Do you guys know? Let's try to do this without looking it up. Let's see, is there any way that, like, do you know the inch to centimeter conversion? 2.54. Very good. Okay, so we have an inch on the bottom. .54 centimeters. Okay, but the problem is that it's not cubed. Yeah, you could do it 3 times. So you could do a cube here, and a cube there. So you don't forget to cube the number. Okay, so if you cube everything, then you've got it. You've gotten out of inches cubed and into cubic centimeters. Now let's do liters, since we're going to later use like the gas constant and get into the so on. So how many cubic centimeters do we have per liter?
1 cc is 1
milliliter. Yeah. So 1 cc is 1. So we have 1,000 centimeters cubed is 1 liter. So now we've got our volume A in terms of liters. Okay. So someone want to calculate that? Let me check to make sure. Yeah, just 3 significant figures would be good. 6.55. All right, 6.55 liters. That's volume A. And let's calculate volume C. Times 8.3.
Oh wait, I didn't do the RC minus 1 part. I just did the top one.
Oh, okay,
So
good. Yeah, gotcha. Yeah, I was wondering, that seemed pretty high.
Sorry, I just did the top part.
That's fine. Yeah, that was the volume of the displacement. Yeah. Okay, so what was it? 0.888 liters. And so then 8 times that would be VC. 7 point what? Okay. 7.11. Yeah. You got what?
0.888 times 8.38 is 7.44.
Oh, really? Okay. Okay. For 4. Okay, so there's our 2 liters our two volumes, and does it make sense? Volume A should be less than volume C, and it is. Okay, so here's our smallest volume, here's our largest volume. So in our Carnot cycle, it looks like that. Oh, that's ugly. This is 7, and this is 0.8. So that makes sense. Okay, those are the farthest points on our Carnot cycle. Now, I don't know about my temperatures. Okay, so how do you get accurate temperatures for a combustion engine? I just really don't know. And so I Googled some things and what have you, but are these realistic? I don't really know. Okay, so that's where this kind of falls down. I would love to know what range of temperatures we have in our engine. I don't think it makes sense to have the intake come in at room temperature because the engine's warm. And so all of those gases, they're going into a hot space. They're probably warming up on the way. So whatever the low temperature is and the high temperature is, I really don't know. So I do know that I put some of these temperatures in and move things around so that the Carnot cycle that we see plotted is really nice. Some of these are so thin and so close together that you really can't see that they look like a Carnot cycle. So with these temperatures, we have a nice spread out cycle. So I'll just put question marks by those as to whether they're relevant, but those are the temperatures that we're going to go with. So 1780 Kelvin and 1350 Kelvin. Just so that you can quickly convert those into your head, that's 1,000 degrees Celsius and 1,500 degrees Celsius, or 1,971 Fahrenheit or 2,745 Fahrenheit. So those are pretty hot temperatures. Are they realistic? Again, I'm not so sure. You're getting pretty close to, softening the metal in some places, and that's why we need to cool these engines. Now, the metals have a low heat capacity, so they pass their heat onto water pretty fast, but, we'll see. Now, as far as the moles of gas, we could do the sort of ideal gas law and everything at these temperatures and see what kind of moles of gas we would have. And so all of this displacement, and so this is a fairly reasonable amount of gas that we're putting in there. So we're using linear molecules as a working fluid. So nitrogen, oxygen, CO2 is linear. So water will be the only thing that's not linear in this. And so the water of combustion. But for pushing that piston, we'll use linear molecules as a working fluid. And so these are the questions that we want to ask. How much work is produced by this engine by one rotation of all 8 cylinders? That takes, in a real engine, multiple rotations, but if you had all of them in sync and they all pulled down and all pushed up, that would be one sort of practical rotation of the engine. How much work is produced by one of those, and then how much heat is consumed, and what's the efficiency. And it says compute both ways. So if I were to have that on the test, what am I talking about that? With computing the efficiency both ways. It's for a Carnot cycle for sure. Well, for Carnot cycle, there's 2 ways to compute the efficiency. In fact, one of them we could do right now. What's that? Yeah, so the heat in, so we have the work, it was on this previous slide here at the bottom, right? We could take the work of the cycle and divide by the heat in. So that's one way of calculating the efficiency, but there's a second way. So this is a great equation. So if we have the temperatures, we could calculate the efficiency right away. So that's the second way. So we'll calculate the efficiency both ways. And and that's also, if you take the chemistry GRE, that's definitely going to be one of the calculations. You'll have this problem that is scary, and it's got all of these temperatures and pressures and everything like that. And it says, calculate the efficiency of this engine. All you need is to find the 2 temperatures in that problem, and you can calculate it. Or you could spend 30 minutes trying to work out all of the works and the heats and everything like that and calculate it that way and waste a lot of time. And so it's almost a trick question to have all of this extra information, like the compression ratio and everything, when all you really need is a hot and a cold temperature, and you can calculate the efficiency of the engine. So we can do that here. So efficiency one way here, efficiency is equal to 1 minus 1350 over 1780. And always, always, always in Kelvin. Okay. So what is that efficiency?
24%.
Yeah, 0.24. Yeah, so 24% efficient, which is pretty good. It doesn't sound good, but that's pretty good. It's a depressing part of science. The 24 is good. Okay, so so we have our state variables table. Our VA was 0.888. And this was, BC was, help me out again. BC was, 7.44. Our hot temperature was 1780. And our cold temperature was 1350. And this is a new chart for you here. I went ahead and put the actual chart for these data points. And so we could look at it, and this is the way it'll be on the exam too. Like, we can check our work, and we can look at this graph, and we can say, yeah, that looks like 0.88, right? And this looks like 7.4. So we got some good numbers here. The hot, we can't see the temperatures on here. Now, here's where you make your first mistake if you're not paying attention, and that is to put the 1350 here. B is at the hot temperature, so it's 1780. I see that so many times that people mess up the temperatures. Okay, so that this whole line right here is at 1780, which means B is also at 1780, and this one is at 1350. Can you at least see that? Those are your isotherms, and so those have two temperatures, and so then you know what points have what temperature. There's also a nice way to people try to trick you in thermodynamic calculations. They'll say a temperature in Celsius. They'll say 50 degrees Celsius and then doubled at 100 degrees Celsius. That's not twice. That's not doubling the temperature. Kelvin is the absolute temperature scale. And so you're going from 50 plus 273 to 100 plus 273. And so that's a pretty small change. It's not doubling the temperature. So that's another trick that people play. Anyway, just telling you all the secrets. Then let's, these are the adiabatic relationships here. So let's go ahead and do those next to get volume B and volume C. Does that make sense? So we have this situation where we've got this relationship to get volume B. Volume B here is connected to point C by an adiabat. Okay. And so we can use that adiabatic relationship with our volumes. And so I have the temperature at B, which is 1780 here, and the temperature at C, which is 13, so it's cooling down, 1350, so it's cooling down. And then I have 1 over gamma minus 1, so we've got to figure out what gamma is. So we have a linear set of molecules, and so let's do our CV first. Translation was 3/2 R plus 2/2 R for rotation. And then up here, it's 3/2 plus 2/2 plus another 2/2 R. So my R's all cancel. My halves all cancel. And so I have 3, 4, 5, 6, 7 on top and 5 on bottom, 7/5.
Should be like 1.4.
Mm-hmm. There we go. So the gamma is 1.4 for a linear molecule. We had that table earlier with all three. We had the monatomic was 1.67, the linear was 1.4, and then the bent or more complicated molecules was 1.33. What was it? Oh, I thought you had it on your little notes there. Okay, so that's our 1.4. So sometimes I leave it in terms of like the 7/5 because 7/5 minus 1 is 7/5 minus 5/5, which is equal to 2/5, right? Okay, and then 1 over that is 5. So 1 over gamma minus 1 then is 5 over 2. And so then this is raised to the 5/2 power. Does that make sense? Yeah, so this is gamma, this is minus 1, and then you just invert that, you get 5/2. And so then I can raise this temperature ratio to the 5/2 power. Okay. So it's less than 1, it's raised to a power that's greater than 1, so it should be, again, a less than 1 thing times C, so I'm going to shrink that volume C down to make a volume B. Volume C was 7.44. And so then this power here was 5 over 2. So does everybody see all the numbers? We have 1350 over 1780. Okay. You could do the y to the x key and put in a 5, and then you could take the square root, and then you get that fraction. You multiply that by 7.44, and then you get the volume B. So what did you end up with?
3.726.
Okay, good. 3.73. And does that look right? We look at our chart. Yeah, that looks pretty good. 3.7. So we've done that. We've got the right relationship, and we got the right B. Okay. And then we can do the same thing here for this one. Now the volume D is connected to volume A with an adiabat. $1.77? Okay. So let's just put our numbers in here though. Since it's connected to A, we have the temperature of A. So now 1780 on top and 1350 on bottom. Okay. Still raised to the 5/2 power. And BA was 0.888. So those are all your numbers for that calculation. Multiply it all, you get 1.77. So now we have 2 full columns of our state variables table, and we can do the ideal gas law to get all our pressures. Again, making sure you have your correct temperatures. We can calculate our pressures. Number of moles was 0.05. Gas constant, which one are you going to use here? 0.08206 liters atmospheres per mole Kelvin. That way we cancel the moles, we cancel the Kelvin from the temperatures, we're dividing by the volume, and so we're left with atmospheres. So that's good. We have the hot temperature, and then we're divided by 0.888. So what's our first pressure? Two. Okay. What about this one? It's essentially that same calculation, but you're dividing by a bigger volume. So what do you have for this one? Okay, 1.95. I've got them all written here. 0.7 for C, 0.74, and D, 3.13. So our state variable table is full. That's what we need to calculate our delta T's and our delta V's and so on for the work. We have our pressures. If we didn't have the plot, we couldn't check our work, but we could plot it and just make sure that volume D here and B are between A and C. So A is our smallest volume. So we look at our table, we see that A is the smallest volume in the table, C is the largest volume in the table. So that checks out. Our pressures, A has to be the highest pressure, and it is. C has to be the lowest pressure, and it is. So y'all are catching, what I'm saying about all of these different parts of the process. And then if your temperatures for A and B are the same in the hot temperature, and then C and D, same temperature, but the cold temperature. So those are three relationships that you can use to check your table. A is the highest pressure and the smallest volume. C is the smallest pressure, the highest volume. So those are two principles. And then the temperatures are hot, A and B, and the cold temperature is C and D. If you've got all those things worked out, you probably have a correct state variables table. And then we can move on to calculating all of the work in the heat and so on. Okay, so here's our state variables table. I can fill it out. Essentially, we just did that on the previous slide. So I'm going to skip to the next one and calculate all of our work in heat. So for the isothermal expansion piece, the work for leg A to B, $17.80. I don't know why I can't remember that number. So there's the NRT, natural log. So VB is 3.73, and BA was 0.888. So our liters cancel. We have this fraction that's greater than 1. So our natural log will be greater than 1. We have all of these other terms. And then we have this minus sign. So again, this is the work of the system. For an expansion, it does work on the surroundings. So it's to be a negative number. So that's where that negative sign comes from. Don't drop it because the signs matter in this calculation. And again, just the numbers in 3 significant figures would be enough. Uh-oh. Let's go back to the laptop. Okay, good. All right, somebody give me some numbers here.
Negative
68, 107. Joules. Okay. All right, and then I mean you can keep those keep all of the digits that you want for calculating further down, but I'm just writing down 3 significant for our reporting values. Okay, then what else? we do the next one, so the adiabatic expansion, or do you want to do the compression next? Since we are doing the same equation, let's do the compression next. Okay, so then we have minus 0.050 moles, 8.314 joules per mole Kelvin. Here's the cold temperature now, 1350. So this has a minus sign in front of it, but the compression should have a positive sign. Where's that minus sign go? It's because this fraction inside the log is less than 1. So we're doing a compression, so the V final is smaller than V initial, so this fraction is less than 1. And so then that gives us a negative sign on the log, the natural log. So we have volume D is 1.77. And this is connected to volume C, 7.44. So that will produce a negative natural log, and then that'll kill that minus sign at the beginning. Okay, so leg CD, the work, you get 800 and something. What do you have? 8 what?
806.
806, okay. Okay, excellent. Positive number, that's good. So now let's do the adiabatic expansion. CV, since it's a linear molecule, is what again? Mm-hmm. Good. So 5 halves. R. Well, let's go ahead and write R out since we're doing the calculation. 5 halves times 8.314. And then T final minus T initial. This is leg B to C. So so we're going, the final is temperature of C. So that's 1350 minus 1780. That, you know, the small number is subtracting the larger number, so that's going to be negative, and that's good because we're doing an expansion, so we should have a negative amount of work. Okay. Now look at the adiabatic compression. This is exactly the same formula, only swap the temperatures. If you swap the temperatures, you swap the sign. Yeah. So this is equal to the opposite sign of work of BC. And so it's positive 447. Okay. We could do the heat amounts too. Up here at this first one, this isothermal expansion, remember the temperature was the same, so we had a zero change in internal energy. So Q AB is equal to the minus WAB. So it's 1070 joules. So that's the Q. We put in a 1,000 joules to get 1,000 joules of work out of that leg. Q for the adiabatic expansion is 0. Down here, Q for the adiabatic compression is 0. And then here, Q for CD is equal to minus 806. So in order to compress it, we put in 800 joules, but to keep it isothermal, we had to take those 800 joules of heat out. So while we're compressing it, we're sinking that heat by having it in contact with a cold reservoir. So we're pushing on that gas, and it's wanting to heat up, but it's losing its heat to the environment as it's being compressed. So these are all of our heat and work values for the whole cycle. That's fantastic. All we have to work with is temperatures and volumes. We really don't have to worry about the pressures. Okay. So if we add all these together, so for the efficiency, we have, we add all four of these for the net work. Okay, and we take the absolute value, so our efficiency is a positive number. Okay, so adding all of that up, we end up with the absolute value of, let me see. And it's 0. Oh, that's in kilojoules. But I want you all to add them up. So we have, start with the positive ones, it'll be easier. So 806 joules plus 447 joules, and then subtract the 447, so that's a wash, and then subtract 1070. So really 806 minus 1070. So we get the same efficiency that we got with the temperatures. So that's satisfying. After doing all of this math, we get to the same endpoint. Okay, so it's a 24% efficient engine at turning that heat. So we put in 170 joules of energy, and we got like 260 joules of work out. Okay, so, you know, not all engines are going to be this Carnot cycle, but if we have an engine that has, let's say, this blue curve, so like if we have other types of engines, it's still on this map of adiabats and isotherms. And so for computer modeling of real engines, we can take that actual cycle and we can create a bunch of little Carnot cycles and calculate their efficiencies and sort of integrate this loop and figure out what the true efficiency of a true engine is. So even though it sounds like the Carnot cycle may be of limited use, right, because nothing's ever perfectly reversible and so on, and it's not possible to get this, you know, these perfect reversible isotherms and adiabats, we can take an actual cycle and break it up into these little small pieces and integrate the efficiency that way and how much work we get out of actual engines. So we still use it as the sort of perfect modeling device. So here's our basically answer key at the end of the notes. Now, one thing, if you took this whole cycle, and this is how many joules that you get, so 260 joules you get out of one cycle of this engine. So all 8 cylinders have done their thing and produced 260 joules for rotations. How much power can you get out of this engine if you run it at 2,000 RPMs? Right? So you have 2,000 of these per minute, right? So a rotation of the engine is one rotation of the cycle. And so if we do 2,000 of those per minute, how many do we have per second? So that's a minute is 60 seconds. And we have joules per second. We have watts. So this is telling us how many watts we can get out of this engine. So if someone do that calculation, well, actually I got it right here. So we have 30,000 kilowatts that we can get out of this engine, which if you convert to horsepower, that's 41,000 horsepower. So I think my temperatures are off in terms of how much energy I'm getting out of this thing, because 41,000 1,000 horsepower engine, I don't think is accurate. All right, the efficiency may be accurate and so on in terms of what we can get out of this engine, but this is sort of a gut check to see if this makes sense, and it doesn't really make sense. So I know something's wrong with my calculations. I mean, you have 400 cubic inch engines, so I don't think that's unreasonable. Okay, compression ratio, that's a reasonable compression ratio. But what are my temperatures? Because the temperatures really govern how much work you get out, right? Minus the number of moles, which is a reasonable number of moles, times the gas constant, times that hot temperature. That's how much work we're getting out on the hot leg, and the cold temperature too. So I think my temperatures are probably off, and so that's where we're getting this unreasonable amount of power out of this engine. But if this were accurate, wow. So maybe I could take the horsepower for an engine like this and back into the temperatures, because that would be one of the variables that could be easily manipulated. And so since I have this in a spreadsheet, I could do that. I just haven't done it yet. Actually just right now thought about that. And so that would be fun to do. So if you put all these equations in the spreadsheet, you can just play around with them. You can create for yourself practice problems with the Carnot cycle and say, okay, what if the temperatures were this and this? What would all my energies and things be? And if you do it in the spreadsheet, put this one in a spreadsheet so that you got your formulas right, and then change some of the numbers and create your own problem set so that you can check your work. Do that a couple of times, you'll be well prepared for this exam. Okay, so let's go ahead and get an attendance so I know that who was here today. So we'll go to Top Hat and do that. So there's our attendance check. But I think that's a good idea. I mean, that's how I practiced problems, would be to sort of set up these scenarios in Excel with a known, like you know the answer is here for this problem, and then you can use that to make sure your equations are right, and then change your temperatures, change your number of moles, and then you can check your work.